Hello, I am Jordi Triquell and I would like to present you the IBM Advanced Data Science Capstone project in Coursera. My project is about recognizing traffic signs in a self-driving car context. The presentation is divided into two parts. The first one is addressed to stakeholders, where I present the use case and the project results. And the second one is addressed to my data science peers, and I talk about the technical decisions that I made to achieve the final results. So let's start it. I hope you will enjoy it. Let's start with a stakeholders presentation. My use case is about recognizing traffic signs. This information is going to be used in a motion planning software of a self-driving car. Therefore, it's important that traffic signs are recognized with high accuracy as there are human lives at risk. The scope of the project is not to detect and find traffic signs in a bigger image. This should be done in a previous step that is not considered in this project. So the project is only about recognizing traffic signs that have already been detected in a bigger image. The goal of this project is to train a model using images of previously labeled traffic signs. My source dataset is obtained from the German traffic recognition benchmarks with 43 types of traffic signs. This is a dataset that can be obtained from many sources, and I choose one from kaggle.com that had already processed and labeled the images and separated them into training, validation, and test datasets. A significant part of the images has very low quality and noise due to motion blur, insufficient light, and other causes. This shouldn't be considered a problem of the dataset, as it is expected that in a real scenario, lots of images are going to have this kind of defects. My solution to the use case includes creating and evaluating two models using machine learning techniques, one using logistic regression and another one using a convolutional neural network. As it was expected, the convolutional neural network gave the best results, with 95% of accuracy in the testing dataset. It can be thought that 95% is not good enough result for a self-driving car software that has the life of its occupants at risk. However, it must be said that a significant part of the wrong predictions in the testing data were hard to predict for a human, at least at first glance, due to the low quality of the images, motion blur, insufficient light, and other causes. Besides, in a real scenario, both a driver and a software do not see only an image but a sequence of images with the same traffic sign. This makes us think that predictions would be better if the testing case included a sequence of images of the same traffic sign, as images with more noise and lower quality will be discarded. Now let's go with the peer presentation. The Kaggle source of the traffic sign had already labeled the images into a dictionary of NumPy arrays, and data was already split into training, validation, and testing. This was a small advantage that saved us from doing an additional data preparation step. The dataset includes more than 34,000 images for training, more than 4,000 for validating, and more than 12,000 for testing. And all of them were size 32 per 32 pixels with 3 color channels RGB. There were 43 classes in total, labeled from 0 to 42 for each type of traffic sign. In this case, all the data was labeled without missing values, and some random visualizations showed that all the images were properly labeled. However, some of them had very low quality and noise due to some facts such as motion blur, insufficient light, bad weather, etc. This is not necessarily bad for building a model, as in a real scenario, images are not taken in optimal conditions and they can have these issues. When we analyzed the training dataset, we detected an unbalanced distribution of classes. To prevent that the trained model was better at detecting some kind of traffic signs versus others, we decided to use some data augmentation technique instead of reducing the number of samples of the most frequent signs. This was done by adding some random sliding rotations and adjusting brightness in the training samples of the least frequent classes. After carrying out this step, the data distribution was equalized in all the classes, as it can be seen in the plot. In addition to this, we detected that data was perfectly sorted and therefore it was shuffled to carry out a proper training, as the stochastic and batch training algorithms only use a part of the training data in every iteration, and therefore it is better that they are randomly sorted to enhance faster conversions and performance. As input data only consists of values of each color channel in each pixel, we opted by normalizing dataset by dividing by 255 instead of using the average and standard deviation. This is a common way to normalize many datasets consisting only of images instead of calculating mean and standard deviation. When we talk about infrastructure, I have to tell that I use IBM Watson Studio for the exploratory analysis and feature engineering, but I was forced to use my local PC with Anaconda in order to train my model at a higher speed. IBM Lite free plan with one CPU and 4 GB RAM proved to be insufficient because the dataset size was very big and also the number of classes to train. Libraries that I used were sklearn and Keras, as they are open source and very reputable in the data science community. In this case, Keras used TensorFlow library as backend. sklearn was used for training a model that uses a logistic regression, and Keras with TensorFlow for a model that uses a convolutional neural network. Let's talk about the logistic regression model. I use first a standard scaler to normalize data. In the second step, I applied PCA, principal component analysis, to reduce the number of features, keeping the components that retain a 95% of the variance, as I found that the model was very slow to train without doing that. Finally, I applied logistic regression. At the end, I got a result of 77% of accuracy in the testing dataset, which from my point of view is surprising, as I consider that it is very high for this type of model. For the convolutional neural network, I created a model with 3 convolutional layers with a ReLU activation function. Each convolutional layer was followed by a max pooling layer to speed up training. I also add dropout on the second and third convolutional layers to prevent overfitting. And these convolutional layers had the mission of learning the features that are critical for the model. These layers were followed by 3 dense layers with the mission of classifying the model. The first 2 dense layers used a ReLU activation function and dropout, but the last one used softmax, as is the de facto activation function for multi-classification models. This is some sample of the code that I used to build a model of the convolutional neural network with Keras. As we can see, the first convolution has 32 filters and a kernel size of 3. The second convolution has 64 filters and a kernel size of 9, and the third one 128 filters and a kernel size of 18. Increasing the kernel size and the number of filters in every successive layer is common in most of COMNETs, as first layer's purpose is learning low-level features such as edges, and the successive layers learn more complex high-level features. Finally, the result is connected to a network of fully connected or dense layer. In this case, we have used ReLU for the first 2 layers and a softmax for the last one, as this is the best activation function for multi-classification, like it is this use case. As it can also be seen, I have also added dropout in most layers to reduce slightly overfitting. This gives us more than 3 million of trainable parameters. Other technical decisions were reducing the learning rate at each epoch, by using a learning rate scheduler, and also save the weights at every epoch. As epochs increase, the performance of the training dataset always improves, but not necessarily for the validation dataset, as the model might overfit. The idea is using early stopping by choosing the model weights that performs better with the validation dataset among all the epochs. These decisions also allows us to prevent overfitting. We plotted accuracy and the loss at every epoch, and we can see that the model converged pretty fast with no significant improvement in the reduction of the loss in the validation set after the second epoch. Now let's do model evaluation. As the use case is classification model, we decided to use accuracy as a performance indicator. This is a summary with the results of the two trained models. As expected, convolutional neural network was superior to logistic regression, as logistic regression can capture the patterns required to recognize a traffic sign. However, logistic regression gave us an accuracy of 77%, which was much higher than I expected. On the other hand, convolutional neural network gives a pretty good performance of 95% of accuracy. Considering that this is a use case that must be used in a self-driving car and there are lives at risk, maybe we can think that 95% of accuracy is not good enough. We analyzed some random wrong predictions in the test dataset of the convolutional neural network, and we saw that a significant part of the wrong predictions were even harder for a human to predict due to low quality of the images, as you can see in this slide. Therefore, we do not consider a 95% of accuracy a bad result. And besides, a real case scenario would include several images of the same traffic sign, as there is a camera constantly recording. So it is probably that low quality images will be discarded somehow. Now, to summarize, I think I set up a decent model. As it was expected, the convolutional neural network works best in this image recognition task. We can consider 95% of accuracy as a good result, as a significant part of the wrong predictions do not have good quality and even in some cases are harder for a human to distinguish at first glance. So I see this part of the project as concluded. As a future research, I see further tasks such as getting more data traffic sign images of different sources and also training on these images. I also consider trying some other architectures of convolutional neural networks that could lead to better performance. That's all. Thank you very much for your attention.